I have here on the magnetic mat two different types of circuits. The top one right here, this is a series circuit, and this bottom one right here, this is the parallel circuit. There's some important distinctions that we need to understand between the behavior of a parallel circuit compared to a series circuit. There's some different strategies that we need to employ when we're doing diagnostic work on a parallel circuit compared to a series circuit. So we're just going to take a little bit to make sure that we understand the relationship between the two. You'll notice that in these circuits, they share a lot of the same components. So I've got a fuse right here, and a wire, and a latching switch, and some loads. For the most part, they've got the same components in each one. But the thing that you might not be able to pick up very well on the video, but we'll see demonstrated here in a second, is this specific LED. This is actually quite a bit brighter than this one. And this one's actually brighter than this one, but you're not going to be able to see it fully until you experiment on your own magnetic mat. So let's make some measurements to see why that is the case. So this series circuit, we're about to measure the current in the circuit, but as we look at it, there's really only one path for the current to be able to flow through. So there's not an option for the current to go a different path. It has to go that path through the wires and through the load. There's not a secondary path for it to follow. So I have my multimeter here at the top. It's got this little white strip, and that matches the white parts on the multimeter leads, just so we can keep track between the two different multimeters. So we'll just measure some voltage, take some voltage measurements. So let's just measure right here at the load, at the battery source. We're about 12.06. And as I measure down through the series circuit, so I measure here at the battery and then here after the fuse, notice that we'll stay roughly that same value around 12 volts. Okay. When I finally get to this load, something different happens here. So this is 12 volts. When I get to this side, now I have 8 volts. So 4 volts has dropped between this point here and this point here. You should have already watched a video that talked about voltage drop and what that means. So here we have that voltage dropping to 8 volts. So only 8 volts is available for this LED because 4 has dropped here. Okay. Contrary, in a parallel circuit, if I measure the source voltage, I run at 12 volts. And I keep making my way down, roughly stay at 12 volts, and then I get to this thing. And I'm calling this a splice node, but all that it really does is now I have two options. So the current can go up here, or it can go down here, right? And it actually could go out these two ways on these jacks, but in this circuit, really only got these two options. So which option is it going to take is a lot dependent on what's happening after that, but there are two different paths, and so that's what differentiates or signifies this as a parallel circuit. So now we can see that in a parallel circuit, one of the properties are that the voltage, the source voltage, is available for each branch. So this is my top branch here and my bottom branch. Notice that this one has 12 and this one has 12. So our brightness has a lot to do, first of all, with this LED. So this 12 volts right here. This LED only has that 8 volts. These LEDs are the exact same resistance, this one here and this one right here. This LED is the exact same resistance as this LED. This LED had 12 volts, so why isn't it as bright? So to figure that part out, we want to look at the total resistance of the entire circuit. So when we talk about total resistance, if we were to measure that, if we were to put our ohm meter on, and we can't measure resistance with a multimeter and get an accurate value for an LED when it's in the on position, there's a video that discusses that. Why that is the case, but for our purposes, we know our voltage, and we're going to figure out essentially what our total resistance is maybe not the number, but we'll be able to do a comparison between the total resistance of this circuit and the total resistance of this circuit. So think about the resistance from this point here to this point here with the battery disconnected. Okay, so because we can't measure the resistance with an ohm meter and get an accurate representation of what's really happening here, what we're going to do is we're going to measure the current in the circuit. And so on this specific multimeter, I'm going to move this over here. You can't see is underneath this tape, it's showing me I'm going to be measuring milliamps, this lowercase m and uppercase A. And then this, unfortunately, this meter defaults to alternating current, and we're measuring direct current, right? We've got a battery in the circuit. So I have this meter also set up to measure milliamps direct current, and it's measuring the, I have my multimeter leads positioned accordingly. All right, so to measure the current in the circuit, I need to be able to have the current run through the meter. So in order to do that, I can't do like I do when I'm measuring the voltage, right? Let's say if I was measuring the voltage drop right here, I would put 1 meter lead right here and 1 meter lead right here, right? That's not in series, that's actually putting the meter in parallel. So when I measure current in a circuit, I actually have to get into and measure, it has to go through the meter leads and through the meter. That's a lot of times, that's one of the reasons why your meter has a fuse on it, is because the current of the circuit is actually flowing through the meter. So let's connect our meter so that we can measure the current in the circuit. On this series circuit, I'm going to disconnect the latching switch. The latching switch has now been removed from the circuit, and I'm going to connect these meter leads. So we should see our circuit has turned on. The current is now flowing through the meter lead. The red meter lead to the meter, and from the black meter lead back into the circuit. So we've completed our circuit here. We see that our value is 2.5 milliamps of current, and if you are making this measurement and your meter is all over the place in its measurement, it's a good chance you're probably on alternating current, so you want to make sure to check that. In this on this fluke, you can see that it shows DC up in this corner right here, and to turn that on, you're simply just going to push this yellow button. Other meters are going to have different things that you need to do. Okay, we can do the same thing here on this parallel circuit. So let's connect our, and this is the bottom meter, so we're connecting here our leads, and I'm just going to position them so they're a little bit out of the way. Once again, we've opened up the circuit, and now we're forcing those electrons to move through the multimeter and come back out of the multimeter. So the multimeter is essentially counting, if you want to look at it that way or think of it that way, the electrons as they move through the circuit. So the first thing that you should notice is that the current on the top circuit is less than the current on the parallel circuit. So a series circuit with the same components is going to have a higher total resistance, and that higher total resistance is going to cause a decrease in the current in the circuit. I can measure that current really anywhere in the circuit on this series circuit. I just picked this latching switch because it was the easiest place, but if I were to measure it here and remove this fuse, the current should be the same. So the current is the same throughout the entire circuit. On this parallel circuit, we're going to measure the current right here. This part of the circuit, you might notice, there's only one path for the current to flow. So all the current has to flow through this latching switch once we've removed it and gone through the meter. If I were to measure the current, you'll be doing this in your exercises. If I were to measure the current right here, I would really only be measuring the current as it flows through this LED, and the same for this lower LED. So you'll be making that measurement in your worksheets. I just wanted to make you aware of that. When we make those measurements, this value here and this value here should add up to the total current of 14 amps. So the same amount of current that comes in needs to be the same amount of current that is leaving the circuit. When we remove a component from a series circuit, if we had an open right here, notice that the entire circuit has now turned off. So we lose the ability for the circuit to operate. but removing a load in the circuit decreases the total resistance. That decrease in total resistance causes our current, or the amperage measurement that we're reading, to go up. The opposite is true in a parallel circuit. When I disconnect this, we see that the current has gone down. So it's the opposite of a series circuit. So why is that the case? If we think about it right here, think about a whole bunch of electrons kind of piling up right here. And we're moving those electrons, and they had those two options. They could go this direction, or they could go this direction. So just like on a road, when we close a lane, suddenly these electrons are kind of backing up. Now, if you're a theoretical physicist, then you're going to probably argue against that. But for our purposes of diagnosing, we're thinking of those electrons now really only have this one option to move through the circuit. So moving in this direction, we're going to have those electrons now have just this one road to go down. So that has increased the total resistance of the circuit, which then in turn decreases the current that's flowing through the circuit. Okay, so I might run into a problem if I add a load to a parallel circuit. So if this load wasn't intended to be in the circuit, say I have a radio and I want to put the radio in, and I just find a power wire in the car, right? I find 12 volts somewhere and I just tap into that 12 volts. The problem with doing that is now I've decreased the total resistance in the circuit. So this circuit might have been designed to only handle 10 milliamps. And now I've added this additional load, and now I'm running at 14 milliamps. And that's very low for the size of these wires. But a lot of times when a circuit is being designed, they put it just above the minimum requirement for the current that will be flowing through the circuit. So adding an additional device in parallel, like a radio or something, could have negative effects on the circuit. At best case scenario, I just blow the fuse. Worst case scenario, it actually could melt these wires. And so in a parallel circuit, it's important to take into consideration when adding additional branches how that's going to affect the circuit overall. Then hopefully we have a better understanding of the relationship between the resistance in the circuit and the current flowing through the circuit.